Okay, hi everyone. Thanks for getting back in here on time. So I have the pleasure of introducing the chemistry and toxicology session for today. And I know that these topics can be somewhat on the fringe for a lot of us, but they're so important to understanding PFAS and how we're going to address them and why we need to address them. So looking forward to this session today. For our first talk, unfortunately, we do not have Dr. Chris Teaf with us, but we do have his pre-recorded presentation. So Dr. Teaf is the Director Emeritus at Florida State University, and his talk will be addressing PFAS toxicology risk and recent regulatory considerations.
Good morning. My name is Chris Teaf, and I'm sure that if I was there with you, I would see many familiar faces, and I wish that I was there with you. I appreciate the opportunity to speak this morning, and thanks to Gene Jones and all the conference organizers, staff, and my fellow steering committee members for what I'm sure will be a great PFA forum. What I'll talk about today is a short review of the toxicological, chemical, and risk considerations for members of the chemical class, as well as some recent regulatory releases or guidance that I think many of you may find to be of interest. You will know, you'll know, most of you who are here now, that the PFAs are not achemical. They're a group of chemicals with many names, and it references per and polyfluoroalkyl substances. This represents about 5,000 man-made chemicals that have been in use since the 1940s. These are not found naturally in the environment, although we do find them now in the environment as a result of historical releases. The chlorine-fluorine bond that makes up the skeleton of the PFAs is one of the strongest chemical bonds that we know. And that is referenced in the skeletal structure that you see at the bottom right here. All of the effects, whether they be chemical effects or environmental effects or toxicological effects, vary with chain length, and they vary with the substituent groups that define those effects. So the larger, higher molecular weight substances act differently in the environment due to the smaller, lower molecular weight substances, and so on. There's a great deal of variability in the chemical properties and the toxicity, as many of you may know, and some people will be speaking after I am today on some of those very issues. Of the polyfluorinateds, perfluorooctanoic acid and perfluorooctane sulfonic acid have been the most intensively studied. And that goes back a couple of decades, but more recently it's ramped up tremendously in terms of the research and the scientific publications that are out there. In fact, also there are what we will call emerging substances, emerging PFAs. They're not really emerging anymore, although some still are relatively new to us. Those emerging short chain molecules are getting a lot of attention because of their different chemical and physical and toxicological properties, and that may turn out ultimately to be one of the solutions to the PFA issues. The chemical properties of the polyfluorinated substances are important to the reasons why they're even useful. They repel water and oil very well. They are also good surfactants and dispersants for substances that are not readily dispersed or dissolved in water. Their chemical structure gives them, in many instances, a significant persistence. It can last for decades in certain environmental media, perhaps longer. The most important property that affects what we frequently have to deal with is the water solubility. They are very water soluble for the most part, and that water solubility has everything to do with the potential environmental movement and the potential exposure that we may experience or that individuals may experience to the PFAs. Another interesting chemical physical property is volatility. They're not very volatile, and that combined with as a class, they're not very volatile. There are some that have some volatility, but volatility combined with the water solubility means that they remain in water for a long period of time in normal circumstances. This in turn can affect their long distance mobility, both in, let's say, rainwater or groundwater or surface water. And we are seeing some reports now of distribution in precipitation that may be an explanation for some of the distribution that we see. They have significant bioaccumulation potential, at least some of them do, and that is in part related to their potential toxic effects, which I'll talk about, and then, as I said, others will also cover later on. They were originally used in making of Teflon and similar non-stick products for cookware. Again, this is old news, but I think it's worth remembering why these materials were so widely used and are now so widely found. Also, water-resistant treatments for clothing, carpets, furniture, and those types of things. They also were used in fire retardant foams, which is the subject of some study with regard to exposures in the past, and also the explanation for the sources that we often find in soils and groundwater at areas where fire training was conducted. An interesting sidelight has been the identification of PFAS in turnout gear. That is the equipment used by firefighters during their activities. This turnout gear may serve as a potential exposure source following the exposure to the fire retardant foams. So there may be specific talks about that, but that is an area that we're just now learning about is the persistence in clothing or in firefighting equipment that may result in somewhat unexpected exposures. There have been industrial releases, both permitted and unpermitted. There is water treatment plant release, and the sludges from water treatment plants also have been disposed in landfills or on the ground, which also represents a potential environmental distribution source. Landfills are interesting because they often complicate the question of assigning responsibility for the presence of polyfluorinateds. And they are also found in some foods, drinks, and even household dust as a result of their long-term use. The 5,000 or so chemicals, and it's becoming pretty clear that there are at least this many and perhaps more, makes general statements about these substances difficult. And it makes them difficult because they vary dramatically with chain length and substituent groups, as I mentioned. A great deal of research is ongoing to better understand both of these situations. There are ongoing studies at the federal and the state, and in fact, the private sector level, as well as at universities, such as FSU at the University of Florida, University of Miami, and elsewhere in the US. Exposure determination has become an interesting question. The presence of something isn't necessarily instructive with regard to how dangerous it is. The question is, what's the exposure? Many types of facilities have been demonstrated to have PFA issues. Most recently, we're learning more about airports where training was done for fire activities, landfills, because a lot of things go in landfills that we maybe historically did not fully understand, and the disposal or the use of textile materials. My primary interest is in the public health impacts, and those very frequently are directed at groundwater and surface water, where the numbers are actually quite low, but it can be an issue for soils as well. And again, some others may talk about this in greater detail. I want to simply introduce the concept that all of these environmental media are potentially of interest. And the science is still emerging, and that will probably be true for a while. With respect to non-cancer potential effects of the PFAS, I'll use PFOA, perfluorooctanoic acid, as the example because it is, as I said, one of the better studied of the group. What has been described so far that seems to have regulatory significance, particularly is the decrease in immune response, delayed skeletal ossification or development of the bone structure in the fetus, which is the basis for the proposed oral reference dose. Secondarily, there have been biochemical effects identified and demonstrated, and these include increased serum cholesterol levels, liver enzyme levels, uric acid, and sort of non-specific kinds of measures like liver weight, which can in fact be indirectly reflective of increased liver enzyme levels, for example. So these are biochemical or biological effects that are identified that the specific significance to the toxicology is really not yet well understood. Delayed mammary gland development has been identified in a variety of studies, and the potential for reduced fetal growth has been identified. One needs to be careful when one looks at the literature here. There's some contradictory information out there, and looking at one study rarely will give you everything that you need to know. And really the place where toxicologists find the greatest degree of difficulty, or in fact interest, is in determining what is present in the way of associations, what effects occur in association with the presence of PFOA, and what are related to the causation of the toxicological effects. And those are not always easily identified. In the cancer reports, there have been a variety of sites: liver, testes, mammary glands, and pancreas. In humans, there are only suggestive links. I'm not aware of any really well-demonstrated links to human cancer. ACGIH considers it to be a confirmed animal carcinogen. IARC considers it to be possible. EPA has a couple of different classifications depending upon when you look. Suggestive is the current classification. As far back as 14 or 15 years, they were considered to be likely potential carcinogens. So keep an eye on that. It's going to change, and it is changing. Here's a variety of research that has been published in the last year or two or three. I think these are useful to look at and gather yourself a good range of data that you can review. Some of these are good reviews. Ted Simon's work in 2019 was a summary report for a large workshop that was done. We published a paper in 2019 that was a summary of sources and chemistry and toxicology and risks. And then a couple of others in 2019 and 20, either from private authors or from the National Toxicology Program, that summarize well issues such as different approaches to risk evaluation, new models for biochemical observed effects, and tumor incidence as it may relate to one sex or the other. A particularly useful, very, very recent document was the CTAC publication that summarized a workshop, and it was published in Environmental Toxicology and Chemistry in March of 2021. You'll see volume 40, issue 3. Here's the title of it. There are 15 articles there that range from environmental chemistry to toxicology to risk assessment and to remediation issues that have been raised or remediation approaches that have been applied. When we look at agency status, and any slide like this that's over about an hour old is probably outdated. So when I say status, this is as of the last month or two, 2021. There currently is no MCL for any of the PFAs, although we believe that they're under development at the present time. EPA has indicated that they are, but I have not seen any documents yet that are released in that regard. The lifetime drinking water health advisory that we are currently operating under is 70 parts per trillion nanograms per liter for the sum of PFOA and PFOS, or the single if only one is present. In early part of 2021, EPA released final regulatory determinations for the PFOA and PFOS, and a toxicity assessment also was released for perfluorobutane sulfonic acid, one that is rising in its level of interest in the toxicology and environmental community. There is debate currently, and it continues, about whether to regulate these polyfluorinated and perfluorinated substances individually, or to continue with the effort to try to regulate them as groups, which is the way that it's being done now, and will probably be that way for a while until enough information gets developed on enough PFAS that we can get beyond that. EPA's action plan has been evolving since the 2018 timeframe, 2018, 19, and then you'll see in a moment 20 and 21. It goes from the original releases of the draft toxicological assessment for one of the smaller molecular weight PFAS, Gen X, and for the polyfluorobutane that I mentioned a minute ago. In the latter part of 2019, method 8327 was released. And this was a useful adjunct because we have the drinking water methods, 533, for example, but there wasn't a good non-potable groundwater or surface water or wastewater method, but that changed in August of 2019. There are people undoubtedly sitting in the room right now listening to me who are involved in that directly, and I would look forward to hearing some of those presentations as the days go on. Systematic review protocols were released for a couple of PFAS, some of the less commonly encountered ones in November of 2019. And this is significant because it's the first step in the IRIS toxicological review process. So that continues now. And then in December of 2019, drinking water method was released, I think, in improved form. And there are now a variety of other PFAS that now have good methods available in 533.1. Continuing on through 2020 and the early part of 2021, EPA announced a proposal to regulate the two common PFAS under the Safe Drinking Water Act. And they are currently researching health effects of 7 more of the most commonly encountered PFAS. Latter part of the year, work group recommendations were made with regard to the NPDES permitting process for PFAS. In December of 2020, interim guidance on destruction and disposal was released. I'm not aware that that's been finalized yet, although there may be someone who's listening who can provide a comment when I'm finished. And then finally, there are methods under development in 2021 for about 40 of the PFAS in a variety of media: wastewater, surface water, groundwater, leachate, soil, sediment, and tissues. So there's a great deal of activity. You're here because you know that. And I would say that it's going to continue in the near future. It's just, there's just a ton of work to be done to try to get enough information to regulate these substances and the range of substances on a reasonable and an accurate basis. In February of 2021, the 5th unregulated contaminant monitoring rule was released, UCMR 5, as we hatefully know it. Sample collection is going to occur for 30 chemicals between 2023 and 2025, so we're a little out still on the data collection and data reporting effort, but it will include a large number of these systems, systems that are providing water in a variety of different circumstances. It also will provide EPA with key data that's needed to understand occurrence and quantities in public drinking water. But as you can tell, it's going to be a number of years before we have this information. So with luck, we'll get interim reports from these, but it's looking like at least 4 or 5 years before we get the final information. So that information was released in February. The 60-day comment period is running like this week or last week. And there have been there are planned for 2 virtual stakeholder meetings once the comments begin to come in. The EPA also reissued its final determination to regulate PFOA and PFOS. They will move forward to implement the National Primary Drinking Water Regulation development. For several others, it's also being proposed at the present time. So in conclusion, and this has been a whirlwind tour of an incredibly large and diverse area of information, PFAS have the potential to cause adverse environmental, ecological, human health effects. I think that has become clear. The question is, to what extent, chemical by chemical, and under what circumstances will those effects express themselves? The difficulty primarily relates to identifying acceptable levels in the face of what is still pretty large uncertainty. And while it's possible to identify protective levels which incorporate large accommodations for this uncertainty, what is not clear is how conservative those are. If they are as conservative as we believe them to be, then in the long run, we may be able to accommodate less restrictive levels, but we simply don't know that at the present time. A variety of agencies at the state and federal and the international level have taken increasingly aggressive approaches. That includes both environmental receptors and human health. And there's a massive assessment, characterization, and evaluation effort underway or on the horizon, as I've given you some examples. And again, I know there are people in the room who will be speaking to this in greater detail, and I look forward to hearing that. The last point I'd like to make, I guess, is that there is large multi-district litigation in progress. Many of you may be familiar with it or even involved in it. That is not likely to be the only one. So keep your eyes peeled. A lot of this information that's being generated has an extreme importance in not only the regulatory status, but also in the litigation status. And with that, I'd like to thank Jean and the symposium organizers for the opportunity to speak today. And I would look forward to you passing on any questions that you have to Jean or to one of the conference folks, and they'll pass them on to me. If you let me know who's providing the question, I will do my best to get in touch with you and answer it.
Okay, so moving along, our next talk is Dr. Zeke. He's a senior engineer with HSW Engineering, and he'll be talking to us about what's behind PFAS toxicity and the state-by-state regulations we're seeing.
Good morning. 1, 2, 3. Zeke field 99, 100. Sounds like I get more time to talk my topic. Yeah, by Taryn. My last name pronounced as her. Just kidding. So I'm going to talk how and why different states we have developed, the values different from EPA health level. How to, Tara, you know how to, okay.
Hold on 1 second.
Thanks. Now I'm losing the screen on that small.
That's not it.
That's mine. Yeah,
Oh, 1 second. Sorry about that.
Me? Is there a way I can control the slide?
There's a,
Okay, here. I'm not going to talk about what PFAS are, how many components in the family. Let me start with CEC, contaminants of emerging concern, or emerging contaminant. In academia, micropollutant or microconstituent are often referred to this group of chemicals. Back to actually 20 years ago, in the USGS had a survey over the US surface water. It indicated a whole bunch pharmaceutical and personal care products. They are present in our surface water, which caused a big ripple at that time. Then if you follow EPA CEC fact sheet, you will find out there are several compounds have been emerging, including 1,4-dioxane perchlorate we have been dealing with at our contaminated site over the last 2 decades. At the bottom, you see the 2 red hot compounds, PFOA and PFAS. You may think the awareness or interest, attention started from 5 years ago after UCMR3 and the EPA health level 70 PPT. Actually, these 2 compounds have been really the focus over the last 20 years. Back to even 70, 80, the manufacturers, they had some studies regarding toxicity already. Polar bear in 2000 already found PFOA, PFAS in their blood. They don't eat pizza, they don't eat popcorn. So it comes from somewhere.
that's not right.
I can't stop.
Hang on one second.
Did I end it?
No, it's
No, I did.
Hold on.
Close. As Dr. Teaf video showed, these 2 compounds are coming to the final stage for drinking water standard improvement. You may not be aware, PFOA and PFAS are the first 2 compounds made to this stage for drinking water regulation for the last also 20 years. Oh, here. Then EPA regulation in water program started actually from 2009 with a provisional health advisory for PFOA 400, PFAS 200 ppts. 2016, we established the lifetime health level 70 ppt for individual and the combined concentration. How low is 70 ppt? It's like a few drops into an Olympic swimming pool. Then later you will realize many states try to cut the few drops to 1 drop, half drop, quarter drop. Then EPA also established regional screening level for groundwater and soil. The click stopped working. Oh, so I'm not going to read through all these numbers. As you can see, this map shows many different states already developed or derived their own standard guideline, screening values, notification levels different from EPA high level. Several states like California, New Jersey, Michigan, they derived their own toxicity data. I'm going to use California as a specific examples. These values are developed really quick, changing like monthly, quarterly. The ITRC PFAS team have been doing a really good job tracking this different state, different agency, even internationally for the values development. The question is, how low is low? How safe is safe? Are we really be concerned with, or should we freaking out or not? Look at this figure. I'm sorry, this looks like my old slides. I'm going, yeah, just still talk through. So this is not the newest version. So as you can see, California, they developed their notification level. Actually, it's 1.7 and 6.5 for PFOA and PFAS. This is based on their toxicity, non-cancer toxicity data. Also, they developed cancer risk data, cancer slope factor for PFOA and PFAS, which is like 4 orders of magnitude different from EPA cancer risk for PFOA. So based on those numbers, their risk-based level will be 0.1 and 0.4 ppts. Obviously, these values are below the laboratory or instrument detection limit at this moment. So there's no point to make this number at a regulatory or cleanup target level. So California established notification level for 5 and 7 for these 2 compounds. Their cleanup target level or enforceable level is 10 and 40. So which give the stakeholders some, buffering capacity. Like I said, how safe is safe, how low is low? Based on the US population, our blood concentration over since 2000, since 1990, the level has been, decreased since we phased out PFAS and PFOA. However, you can see those levels is in ppb level. I had something in the new PowerPoint, the 3M workers or the DuPont workers, their level, is 2,000 or 4,000 ppb level. That's why and how they can correlate the adverse health effect to their blood level. For our, in my body, probably you can find 100 ppb, 100 ppt, maybe 1,000 ppt level, but no way it's close to 1 ppb levels. So we know everything, nothing is non-toxic. Everything is toxic based on the dose, how much you drink, how much you eat. I'm not going to talk through all these equations, parameters. However, I would like to point out for all kinds of values, they were derived based on the toxicity data and exposure scenario. How much we drink, then how toxic the chemicals. The challenging for toxicity values, why different states, derived different values, because there are so many toxicity studies with inconsistent results. Human being, we got large population, with this compound in our blood, but there is no scientific way to correlate our toxicity to our human body data because, you know, we don't have a starting point. When was the maximum, you know, dose in our body? So we have to rely on animal toxicity study, or called in vivo study. From here, the animal study transfer to human study. There is a big uncertainty factor for several phases, which can be, you know, from 30 to 1,000 level. So the toxicity value, as you can see, for non-cancer value can be 100 times different between the California value and the EPA health value, which caused the, I'm going to skip this. So we may have, you know, this state use 2 liters per day drinking water consumption. EPA use 2.5, another state may use, you know, 1.8. All these parameters will cause some variation in the values, but still with, you know, 20–30% range. So the main uncertainty is the toxicity value. I'm losing a lot of new slides, and so how do these new values, different values, really affect our business, the responsible for party and, you know, stakeholder? I have an example here. You can see based on 70 ppt, we are able to delineate the site groundwater plume. However, if the number goes down to 10 or 5, like California, we're going to chase around these 2 compounds everywhere across the site. And very likely, I cannot point to the top left corner. We're going to reopen some other site nearby. The bottom left figure shows the treatment capacity or breakthrough curve for anion exchange resin. Let's focus on the green curve, which is the PFAS. Based on the breakthrough value for 70 ppd versus 10 ppt, the change out frequency can be doubled, and obviously the O&M costs will be doubled. So what if, you know, what's the pro and cons use 70 today? Probably many of our clients will be happy. Okay, I don't need to do too much work at this moment. So I can discharge my pump and treat water at 70 ppt to another pond, to another infiltration galleries. 5 years later, if the value drops to 10, now you will have a large plume or large liability to take over at that time. Oh, so other than the water criteria or values, we have soil leachability value. I would not talk about the 1.3 or 25 ppm, you know, direct exposure level. Going to focus on the leachability level. Why they are different between EPA's and our Florida provisional levels, or even some other states. As you can see, EPA used end point of value for groundwater is 400 ppts. Florida, we use 70. Actually, it benefits them, this value. However, you can see their KOC value, which is the factor, you know, determine how much PFAS or PFOA will stay in soil. Their level is 5 times different, lower than the values Florida used. Also, they don't have a dilution factor. That's how their regional screening level is down to less than single digit level. It's below actually detection limit. close to detection limit or urban background level. If we use the EPA's KOC value and Florida's approach, the leachability level value can be 0.6 and 1.3 for these two compounds. Which values really represent the real world scenarios? We don't have a large quantity of data, large amount of data. Maybe Dr. Thompson from UF, they have statewide data. Based on our limited data, we see PFOA using our standard SPLP method. The leachability at 70 ppt is around 2 microgram per kilogram. However, PFAS, we see much lower than 7 microgram per kilogram. Please be aware this standard SPLP method is not designed specifically for PFAS and PFOA because the unique chemical property of these two compounds, they have a hydrophobic tail, which is similar to majority of our traditional contaminants like petroleum or PCE, TCE. Their sorption or fate transport primarily dominated by KOC and soil FOC. These two compounds, they both have a hydrophilic head, which means they like water, don't like soil. And also they are negatively charged. Our natural soil at neutral pH, mostly they are negatively charged. So negative against negative, the electrostatic repulsion will work against the hydrophobic sorption. That's why different studies based on the ITRT survey, large literature review, it found in natural condition or contaminated sites, the KOC value are reported with a big range, by order or 20 times difference. That's why we may see different sites, you see different groundwater impact, although you see, oh, my soil has no impact below leachability standard. Why I still have groundwater impact? That's because these two compounds are different. They don't have a unique KOC value. Additionally, because they have a different KOC value or they have a different solubility value, so they can be transport or migrate in groundwater totally different at a different site based on the soil characteristics. Just based on the KOC value used by EPA and DEP, you can expect the groundwater plume can be 5 times the difference. So caution should be taken if you try to use traditional analytical or numerical model to predict how far. Oh, you can confirm or promise your clients the plume wouldn't be beyond 50 feet based on the KOC 500. Actually, it could. Thank you. Probably you have seen this two, analogy many times. I would like to point out, to the left side of picture, iceberg. Although we don't know the exact shape, under the water table. However, we have knowledge already. We know what molecular structure. We know how much, above water table, below water table. We know the temperature, we know the salinity level, so we can calculate it out. On the right hand of the PFAS pyramid actually doesn't represent the real complexity of this family class, compounds, because not only toxicity, we don't even know what what they are, who they are, when they were manufactured and used in what type of industry or processes. So a long way to go if we need to finish study of the full set or family of PFAS compounds. So what's next regarding or in perspective of toxicity or regulation? I'm sure there will be other presentations talk about many programs on the DEP, but I'm just focused on water here, as I presented earlier. EPA is in final stage evaluate MCL for these two compounds, which could take 3.5 years and can be 5 years, may end up with no MCL. However, if the MCL for these two compounds established, that means all the municipality will need to meet the compliance, monitoring, treatment as needed. Also, as I think Dr. Thompson's presentation, the toxicity characteristic, 100 times the MCL, typically that will be our tick-leap hazardous waste level. That means if the MCL established at 70, then 7 ppb will be the hazardous level. If EPA established at 40 or 30, then for MCL, then the hazardous level will be lower. That means majority of our AFFF site could end up with hazardous level groundwater plume. Also, the circular and regular, they are working on designate these two compounds as hazardous substance or hazardous waste, which can cause, enforceable cleanup. EPA is also working on the toxicity value for other compounds. You may be aware 29 PFAS compounds will be in the UCMR 5 monitoring cycle. So 5 years later, there will be another big topic regarding more PFAS in regulation process. And I'm going to talk about the surface criteria. So just like drinking water and groundwater, there will be more large range of value developed for surface water because the different fish consumption capacity amount for human being health, and more about the big range for bioaccumulation factor for ecosystem, how the aquatic system will be affected by these two compounds. Then the toxicity of a PFAS mixture. This will be a mystery never be solved. Not only PFAS, it's just any compounds, the synergistic, health effect for a mixture is going to be really, really hard. Firstly, let's solve individual compounds. How can we get this over 4,700 or 6,300 PFAS compound toxicity? I guarantee there will be no way, in our lifetime we finish toxicity study for all these chemicals. So EPA actually has been funding a new research on a new method called a NAM. You may think it's a natural attenuation monitoring. Actually not, it's called new approach methodologies, which they collect large quantity of existing toxicity data. What's the level? What's the trigger to molecular cell? Then combined with computer calculation of molecular structure and the toxicity value called big data. They try to, predict whether or not we can use a group of toxicity based on the molecular structure. That will be coming in the future. Please be aware, we are all essential. So no matter how we regulate, PFAS compounds not only PFOA and PFAS, they will be used, they will be needed in our product or some process. It all depends on the rural policymaker, whether or not we need to wear a mask. How do we wear a mask? What kind of mask we should wear? I'm going to stop here, then I guess question in the end.
Okay, thank you, Zeke. Okay, our next speaker is with us today, Dr. Ronald Kotun, Senior Toxicologist with Tetra Tech, and he'll be speaking to us about the variability in PFAS toxicity values and its impact on regulating risk. Thank you.
Good morning. How does it feel to be mask-free? Yeah, and wear dress clothes for a change. So, well, it's wonderful to actually be in a crowd of people. I'm really happy to be here. So I'm going to talk about variability in PFAS toxicity values and its impact on risk evaluation of sites. And it's going to sort of piggyback off of some of what Zeke talked about. And I'll probably go into a little more detail. I hope it doesn't get too geeky for you. We're going to try to maybe give you some terms from a toxicological standpoint, and just to try to get a better handle on why New Jersey is so different than others, let's say Florida or Pennsylvania or Michigan, for example. So, okay, what do I have to hit here? There we go. So just as an introduction, I've been with Tetra Tech for 22 years. And I've been in the environmental industry since the advent of Superfund, so in the late 80s there. And my background's in pharmacology and toxicology and a BS in chemistry. And I've been doing risk assessment since its advent, and when RAGS came out in 1989. So, I've done work on behalf of industrial clients. I've done work on behalf of DOD, and worked across the nation dealing with various regulatory criteria and just different regulations from state to state, whether it be with regards to CERCLA, to RCRA, to brownfield type regulations. So general presentation today, I'm going to talk about the variable criteria. We've already seen some of that presented by Zeke. And then we're going to dive into a little more. I want to show you why why is there this variability? And a lot of it has to do with how the toxicity factors are developed. Some of it has to do with who is being considered the sensitive receptor. So who is being exposed? And would you want to base it on a child's exposure? Do we want to base it on an adult's exposure? And then we're going to assess that variability to understand how we see those changes. So we'll get into a little bit about the equations here. So just bear with me as we go through all this. This is just a graph showing, and I'm just going to be focusing on, in general, PFAS, PFOS, and PFOA, PFOA, and the drinking water criteria that exist out there. And look at the bar graphs that I have here. So, I mean, we see, extremely high levels, let's say, criteria in Texas, if I can read that right, and then, we know that the EPA's lifetime health advisory is 70. But other states are coming up with more criteria that are much more sensitive. And we've seen that in New Jersey and, of course, in California. Florida pretty much has, in their provisional GCTLs, groundwater cleanup target levels, have stayed with EPA's lifetime health advisories. What's also interesting is that, Florida, has taken it a step further with some provisional values, getting into irrigation water, surface water, and of course some soil levels protective of direct contact, and soil levels protective of leaching to groundwater to be protective of GCTLs. So looking at that graph, why is it so variable? And am I really safer, being in New Jersey versus, let's say the state of Florida, because the levels are lower? And like I said, it's all contingent on how the number is calculated. And I want to try to give you that backup so you can have a better understanding of how it comes to be. So Well, first of all, we can look state by state, and what we can find is a different, some of you, I don't know, you may be, if you're familiar with risk assessment, and we're not going to focus on cancer so much, I want to focus on the non-cancer effects. We have a toxicity factor called a reference dose. So it's really telling me how much can I take into my body that will cause or trigger some threshold concentration that's going to help me elicit, or that's going to allow me to elicit some kind of toxic effect. So there's different tox values that can be developed for any individual PFAS compound. There's maybe a different way of how that toxicity value is derived. And then of course, we know this is an emerging contaminant, and all of these PFAS compounds are continuously being studied more intensely now. So there's going to be an evolution of the science. And over time, we may have more toxicological data out there in the literature that's going to help us drive and ultimately revise what the most appropriate toxicity factor is going to be. And ultimately, the toxicologists gather together in their conference rooms in these different regulatory agencies, and they're going to come to some consensus decision on what's the appropriate toxicological study to use, what's the appropriate receptor to use to develop a toxicity value for that compound. All right, here's where I get geeky, so don't get scared here. But I just want to, once again, this is going to help give us some perspective. So as a toxicologist, I'm going to be reviewing a study, and we can see the x-axis, we have the dose that's given to, let's say, laboratory mice or rats. And we're going to monitor different effects. And in this case, we're going to look at impacts on the liver, impacts on the central nervous system, and impacts on weight loss. And what we can see here is that, we see higher doses result in greater impacts to the liver. Lower doses result in weight loss. So now it's going to be a determination, well, what do I want to consider as my target effect here? What is the most sensitive, which effect is going to drive my toxicity? And typically we may want to say, well, let's, weight loss is typically considered, a response that may help drive a toxicity factor or the derivation of one. So perhaps in this case, we want to use weight loss, and we can see at a dose of 1 milligram per kilogram per day, there is no effect. But, we bump up to, it looks, roughly around 10 milligrams per kilogram, 3 milligram per kilogram per day, we begin to see some type of a response. And that's where we might see some weight loss. So that might be the dose that's going to help drive the development of that toxicity factor. So in essence, we're looking at a dose response curve. We see here, in this case, we had 5 different doses that were evaluated. But it was the 2 higher doses. It wasn't until we got to those 2 higher doses to begin to see an effect. To have an effective study, we have to have a wide enough dose range, ample sample size. Didn't mean to rhyme there, but that's how it came out. Okay. So, and we want to have obviously some good statistically representative sample to derive a good dose response curve. So the dose there, the lowest dose at which we see an effect is called the low L, the lowest observed adverse effect level. All right. And that dose, the highest the highest dose at where we see no effect is called the no observed adverse effect level. Pretty straightforward. So those 2 doses in the case of this study are going to be the critical values that we want to be using to derive a toxicity factor called the reference dose. So obviously there's some dose in between those 2 is where we begin to see some threshold response, where we see some adverse health effect, whether it be liver impacts or weight loss or anything else that we're measuring. So we've covered the 2 basic terms, low L and the no L. The third one, which is relatively newer in the derivation of toxicity factors, is something called a benchmark dose. And this is a much more sophisticated and much more statistically based way to derive a dose that elicits some kind of an effect. So what we have here, we would have, we can see it, like it said, like a Noel, for example, on here. So we generally, essentially do the same type of study that we did to derive the Noel and Lowell, but we were able to take our toxicity data, our dose response data, input this into a software that statistically derives a specific type of curve, a dose response curve like we see here. And the dose where we get essentially a 10% response, let's say if we're looking at weight loss or some other kind of response, at that point, they call that the benchmark dose. So just for simplicity, it's more of a statistically derived dose, based on the data that we have, rather than focusing solely on the Noel and the Lowell. The Noel and Lowell would be regarded maybe as low tech, whereas the benchmark dose would be much more high tech, much more sophisticated, and tends to have, even though it's more difficult to derive, it provides probably a better assessment of what the impact should be and a better value for deriving a reference dose. So if all of you are familiar with EPA's regional screening levels, or even the FDEP, soil cleanup target levels, and GCTLs, groundwater cleanup target levels, if you look in the technical guidance document for their derivation, you're going to see the reference dose, often called an RFD, which is what we have here. And that's where, this is the basis upon which those values are derived. Now, so we can see with the RFD, we're going to look at a basic algebraic equation here. It's simply one of those values, the Noel, the Lowell, and the benchmark dose, divided by a series of uncertainty factors. Well, what's the basis for these uncertainty factors? In essence, we can look at, if we did an animal study, we're extrapolating those doses in mice or rats to what should be a human equivalent dose. So that's an uncertainty factor that gets applied. So that may be a factor of 10, for example. We account for, in the case of these toxicity studies, we account for super sensitive individuals, a sensitive population. So this could be for children. This could be for pregnant women. It could be for the elderly who have, let's say, less, their metabolic capabilities aren't what they used to be compared to when they're younger. So they may be much more sensitive to the effects of PFAS compounds, for example, than younger adults. So we put an uncertainty factor there. So, there could be extrapolations for, let's say, chronic studies, and typically we're evaluating these values to look at things over the long term. But maybe the study was only done over a year of exposure, and we need to extrapolate that to, for something, a longer term exposure. So we're looking at something maybe from a subchronic exposure to a long-term exposure. So we can add another uncertainty factor there. There are other reasons why we may apply uncertainty factors. But simply put, it's one of those it's the benchmark dose or one of those other toxicity values divided by the uncertainty factors. Another one would be if we decide we're going to use the Lowell, we may have to, we know that the impact, there's a Noel somewhere, but maybe our study just didn't provide a no observed effect dose. So we may want to use an uncertainty factor to get us there. So I sort of just went through those here. All right. So now we're going to delve into the algebraic aspects of this and why we're seeing the variability in the screening levels for these compounds. So in essence, this is a very simplified equation here, but we have our RFD, which is our toxicity factor that we've derived. And essentially the criterion is based on, be contingent on body weight, IR, which is the ingestion rate, how much groundwater or how much, water are we drinking in liters per day. And then there's something called the RSC, the relative source contribution. You may have noticed this on one of the graphs that Zeke presented. And what this is telling us is that, if I'm drinking water at this hotel today, I'm going to drink water elsewhere as well, but perhaps 20% of my water consumption is coming from here. And then 80% of my exposure to maybe a contaminant comes from somewhere else. So I'm being perhaps maybe more sensitive with the derivation of my criterion by saying I get 20% here and 80% elsewhere. So I may have to have a lower concentration. If my only exposure to a contaminant is at this hotel, I'm sure they don't want me to talk that way here, but anyway. And then I'm saying 100% of my intake is coming from the water here, in which case my relative source contribution would be 100% or 1.0 from an equation standpoint here. So this equation here, we're going to show how different factors impact the criterion and why we're seeing the variability from state to state. So here we can say, well, each of us wanted to look at a different study. So we saw different studies were used. You know, EPA, Texas, and Canada looked at rat studies, but New Jersey chose a mouse study. And they each looked at different effects. And so when they calculated their RFDs, of course, they're all different. So we can see in the equation, RFD is in the numerator, and the smaller the reference dose, generally, relatively speaking among compounds, the smaller a dose is, that means we have a lower threshold to have some kind of toxic effect. So the lower the reference dose, it's proportionally directly proportional to criterion. So we have a lower screening level, therefore, for our toxic effects. All right. All right. So some studies, they might use the same study, the same data, but now they're going to look at different receptors. So for example, EPA, in coming up with its 70 part per trillion value for PFAS, uses lactating women as their receptor. Because obviously then they're looking at the ingestion rate of water by a woman that's lactating, as opposed to New Jersey, who focused solely on adult ingestion, or Texas, who therefore focused on child ingestion. And we can see the ingestion rates are different for all of these different receptors. Canada, and I don't know if some of you are familiar, we have standard default exposure assumptions in risk assessment. For residential drinking, I mean, historically it was always 2 liters per day. Now I think it's, it was updated, and I can't remember, I think it's 1.8 liter per day, or 2.3, I'm confused now on that. But nonetheless, it's been updated. But nonetheless, when the RSLs, for example, or the GCTLs are developed, there are standard default exposure assumptions associated with those criteria. So that's hence, in this case, we can see that the adult value in Canada, therefore, differs from what we see in New Jersey. So we can see that by, we see ingestion rate of water in the denominator, the higher that is, if we're taking in more, we're going to have a higher dose, and therefore that's going to lower the criterion. The lower the dose, obviously it can go up. But then we can look at body weight, and we can see therefore a child, obviously has a lower body weight than an adult. So we can see how that algebraically can impact the criterion. So hence more reasons why we may see some different values from state to state or countries or, in any jurisdiction. And then once again, we can just, continue to modify these factors within these equations. So for example, here, we may have the same study that could be used, but remember I talked about those uncertainty factors. If we had a NOEL and a low, we've had the NOEL lower benchmark dose divided by uncertainty factors. You can see here, for example, EPA and Maine used the same uncertainty factors in evaluating a study. But Minnesota, in its derivation of its criteria down below there, has an uncertainty factor of 100. But of course, now they use each of these have used different receptors, and each of them has used a different relative source contribution. Now, I mean, the relative source contribution, just so you're aware, FDEP uses a value of 20% in derivation of its GCTLs to give you perspective. EPA typically uses just a value of 1. So when they're deriving the RSLs, the relative source doesn't really come into play. But nonetheless, we can see how each of these factors algebraically impact the criterion. And therefore, once again, why we're going to see a lot of variability among different jurisdictions. So once again, just to give you a perspective here, not to beat the dead horse, but I'm beating it anyway. We can just see different receptors, different ingestion rates come along with different receptors, and relative source contributions are going to give us different values across the board. So, what we're dealing with here is a lot of science. It's evolving. The studies are becoming more, voluminous here. So I think with regards to EPA's action plan, we're going to see, obviously we're going to, see MCLs probably coming out in the next few years. Nothing happens like that. But, also I focused solely today on PFAS and PFOA, but we're beginning to see more information coming out on, there's been a lack of evidence or studies on, PFBS. EPA just came out with a new tox study for that, the 4 compounds, sulfonic acid. But, there's, multiple PFAS compounds, and how they're ultimately going to be evaluated in mixtures. Right now, it's just an additivity effect. But I don't know if we'll see, there's been some talk about toxicity equivalency, similar to what we've seen with PAHs or PCBs or dioxins. So I don't know how well that will work. It's contingent on how they're going to decide how they're going to evaluate the toxicity factors in doing so, because there needs to be some similarity with regard to toxicity to derive it in that fashion. But it's something to keep an eye on. Zeke mentioned ITRC. Just to keep track of all these variables, they have a fact sheet. It's called Table 4.1. So if you just Google ITRC fact sheets, you'll see Table 4.1, and it provides, it's an evergreen Excel spreadsheet that provides updated values. And so you can see what the values are at any given time. And it has them not only for PFAS and PFOA, but other of the congeners that exist out there. So that's all I got. Thank you.
Thank you for that, Ron. Okay, our last speaker today is joining us virtually. It is Dr. Steve Zemba. He's a project director with Sanborn Head and Associates. And he'll be talking to us today about the PFAS fate and transport, importance of air emissions and deposition, soil, and surface water.
Okay, thank you, Taryn. Let me do a sound and a video check. Are the slides up there, and can you hear me?
Steve, we cannot hear you.
Oh, great. Well, let's see what we can do here. I am not muted. I don't quite understand why you can't hear me.
Steve, hold on just a moment.
Okay.
We got to get your audio going.
Yep. Any luck yet? Testing 789. Well, I can hear you guys, but I guess you can't hear me yet.
Oh, there we go.
Oh, is it live now? Good.
Yep, we got you. Thank you.
You don't know how many times I just hit the mute button. Anyway, very pleased to send my greetings from the frigid state of Vermont, and I'm also happy to be with you, at least virtually today. I'm going to be talking mostly about atmospheric deposition. And it's one thing that, hits PFAS in some sites in particular, and I'll talk about those types of sites. But before I do that, as an outline to my talk, let's see if I can get the pages going here. I'm going to talk a little bit minimally about background, but I wanted to follow up all these great talks on risk assessment with a little discussion of one slide on toxicology, because I think there's a very important development out there right now. Then I'll delve greatly into atmospheric deposition and then come up with some back of the envelope models that, we all can do on literally the back of our envelopes to talk about PFAS fate and transport, and ultimately leave you with the idea that, as sort of Zeke mentioned, soil is a very important thing that I think people need to look at in terms of PFAS reservoirs. So I wanted to follow up on what Ron said. It was a perfect introductory talk, and you would think we practice this because I wanted to talk about PFBS specifically and the value, the reference dose, the non-cancer toxicity values that they just released. There was a draft value that was released in 2018. And the notion has always been that PFBS, which is a 4-carbon short chain PFAS compound, was much less toxic than the compounds we typically focus on, which is PFOA and PFOS, the 8-carbon compounds. And when EPA first proposed its reference dose in 2018, it came out with this value of 20,000 nanograms per kilogram day. Going to change the units on you here. But the value that just came out in the toxicity assessment was reduced 67-fold to 300 nanograms per kilogram day. That is still 15 times less toxic than PFOA and PFOS based on EPA's reference dose values. So it's still less toxic, but it's not 1,000 times less toxic. It's only 15 times less toxic. And from a sort of politico-science perspective, I thought the quote in the press release was very kind of telling and maybe foreboding that, I botched the words there, but I didn't really change the meaning of it. Some people at EPA, I think staff scientists are seeing this now as sort of getting back to science. And if this is where EPA science is going towards lower and more protective reference doses, I would just kind of put out there that, they could be looking, again, especially when you talk about MCLs and looking harder at PFOA and PFOS, and maybe re-examining that reference dose that was used to derive the 70 part per trillion value. If that happens and, EPA starts viewing PFOA and PFOS toxicity more on the lines of, say, some of the states that have come out with the 10 to 20 part per trillion guideline values, we all could be talking about a different game, because 70 parts per trillion might not be good enough anymore. And I'll just leave the risk assessment piece at that. I think this is a very important development. I'm really here to talk about atmospheric deposition. And this is a cartoon figure from I stole from the New Hampshire DES, but it kind of speaks to this issue of what we're talking about. It's pretty obvious, and if you haven't guessed already, it's sources emitting something to the air, usually factories, and then just natural processes, either dry fall to the ground called dry deposition, or rain scavenging pollutants out of the air. The pollutants that are put up into the air return to the ground. With PFAS, this is very important because many of the PFAS compounds don't degrade. So they got to go somewhere, and eventually they're going to come back down to earth. And the other thing that shows in this figure is this idea of soil being an important media. The compounds will deposit to soil and either move straight through the soil, which PFAS, especially the long chain compounds, don't do. They tend to stick around in the soil for a while. But then the soil becomes the reservoir that can impact groundwater for, in some cases, I think, many years to come. We have seen atmospheric deposition before. If you've been around long enough in the environmental or risk assessment world that I live in, we used to talk about things like mercury and dioxins coming out of sources like waste to energy plants. And that's where a lot of the models to look at atmospheric deposition came from. Figure on the left there kind of shows the important difference between wet and dry deposition. If you're talking about a plume from a relatively tall stack, there is no dry deposition right next to the stack because the plume's above your head. But rainfall will scavenge that plume, and the curves on the left figure show the wet deposition being highest right next to the source. That's where the plume is most concentrated, and rainfall will, if you will, take more of it out at that point. Dry deposition takes a while to get down to the ground, for the plume to get down to the ground so it can deposit. So there's this donut hole effect in the dry deposition. And relative, which is more important, wet or dry deposition depends on the pollutant and the pollutant properties, whether it's a particle bound or a gas in those properties. For PFAS, that's something that I think we still need to study for individual sources. Some other thing that becomes important, not so much in Florida where you guys have very little terrain, but in the Northeast where we have a lot of terrain, plume impaction becomes a very important issue. What happens when a plume approaches a mountainside like we have here in Vermont? Does it hit the mountain? Does it go around the mountain? You can get some very high impacts from atmospheric deposition, in this case where plumes interact with terrain. I'm going to go through a couple of case studies. Probably the most studied case study of atmospheric deposition involves a former DuPont manufacturing plant where they used to make Teflon they may even still make it there, but they're not using PFAS in the same way. But this was in, of course, West Virginia, and this was the subject of the Dark Waters movie and the Devil We Know documentary. And what's been studied there have been drinking water impacts around the plant. And those of you who know the Ohio River, you know it flows from the northeast towards the southwest, but the drinking water sources around this plant were affected in all directions, not related in any way to hydrology, more related to atmospheric deposition and transport. And this particular facility, affected drinking water sources to a 20-mile radius. Think about that as a site and what you would have to do with it in that case. And that's kind of what DuPont, is facing at that location. Another DuPont plant in New Jersey. In New Jersey, maybe the third state, I should say. Minnesota had a similar issue with 3M to the DuPont plant back in the early 2000s. Back about 2009, though, people started looking for other sources of this sort. New Jersey found another Teflon manufacturing plant that had atmospheric deposition impacts. And the way you could see that, these are the symbols on this figure show monitoring wells located distances from the industrial facility, which is outlined in yellow. And if you look at the concentrations, you're getting in the hundreds of parts per trillion, nanograms per liter, located quite a different ways away from that yellow industrial site and in directions that don't make any sense from the hydrology. So they figured out pretty quickly that it was atmospheric deposition contributing to the drinking water contamination at these private wells. And fast forward to about 2015-ish, Hoosick Falls, New York, Bennington, Vermont, and Merrimack, New Hampshire, we were facing in the Northeast some different sites dealing with atmospheric deposition or recognized atmospheric deposition problem. These came from coatings of fabric. Basically, fabric was run through a bath to coat it with Teflon. PFAS is added as an additive to those Teflon baths, and when the drying process occurs, the PFAS gets driven off into the stack emissions. This is a particular plant that, for instance, made a lot of the fabric that you see at the Denver airport. So that's kind of what they were producing there, Teflon-coated fabric, and a lot of it. These are individual, again, drinking water wells. Vermont's magic number or guideline is 20 parts per trillion for sum of 5 PFAS. These would be mostly PFOA sources. This is PFOA-dominated plumes because that's the additive that's used in the Teflon baths. And once again, you can see impacts in all directions for miles from the plant. Particularly, there's a ridge to the east of the former manufacturing plant that was particularly hard hit with a lot of different private wells. Again, the costs of dealing with this are quite high. You have to provide basically either a water line to these people and or point of entry treatment systems, which is what's happened in this case. But a very difficult problem to deal with. And those were past plumes. This is actually a current situation. North Carolina DEQ has gone out and literally put out plastic buckets and collected rainwater in various directions from the Chemours manufacturing plant where Gen X is currently made. And there are, by the way, more controls on this plant now, but when they first started looking, they were able to catch the rainwater, analyze it, and find hundreds of parts per trillion of Gen X in the rainwater. So it's a real problem is what I'm trying to say still currently. And some of these PFAS compounds are thought to degrade into other PFAS stable compounds. So maybe we're not completely out of the woods on atmospheric deposition. So far what I've talked about is point sources, large point sources, but even smaller sources can have some atmospheric deposition component associated with them. Encourage you to when you get the copy of these slides, which I'm happy to share, to check out this reference, especially if you're involved in any fire training areas. This was at a refinery in Norway where they did fire training by basically spraying PFAS containing AFFF or film forming foams, aqueous film forming foams onto fires to put them out, which happens, systems in place at airports all over the place and things of that sort. But they tested it and, they did fire training. And what they found when they looked for PFAS in soil, and this is going to be true of a number of the figures I'm going to show you, trying to put units in parts per trillion here in soil. You typically get stuff maybe in parts per billion, but for consistency's sake, I'm going to try and change everything to nanograms per kilogram. Near this source, they were measuring of the order of 10 million parts per trillion, a very high level of PFAS deposition near the source, and that's in the source area. But that was also 52 meters away from where the foam was being applied. And 52 meters, if you look at the picture at the bottom, which is the picture of the fire training area, that's off in the woods. And so 300 feet away at 91 meters, they were still measuring in the million part per trillion range, which is a huge concentration and certainly enough PFAS in soil to drive groundwater plumes. The net point of this is even small sources with spray drift and stuff getting up into the air and traveling even short distances can make your source a lot larger, your soil contamination source, than might be true if you only think about where the foam was applied. So I'm going to run through some quick order of magnitude models just to give some sense of how you might think about these problems in terms of soil being a reservoir. My first question, I answer is, or thought process is, how much PFAS in air do you need to contaminate groundwater? And in the atmospheric deposition world, we have this thing called a deposition velocity, which is kind of related to how a concentration in air will deposit to the ground. You can think of it literally as a velocity. Typical value for a compound might be about, or particles might be about 3 centimeters per second. That's a relatively high value. But the point of this is, if you took PFAS, the question is how much PFAS in air would be needed to deposit just to the ground to account for, say, a level of 1,000 parts per trillion in water. And in the Northeast, we get about 1 meter of rain per year. So if you try and look at what would it take to give you 1,000 nanograms per liter in water, you need about 1 nanogram per cubic meter in air to produce that level. And from perspective, before PFOA was removed from the process at DuPont in West Virginia, they were measuring. There were some spot measurements taken of the order of 70 to 170 nanograms per cubic meter in the air near DuPont. So it kind of makes some sense that there was enough to deposit to the ground there over a wide region to ultimately contaminate water. But it wasn't water that was first contaminated, it was soil. So some other order of magnitude models. And the purpose of this model, by the way, it's based on an air dispersion model in Turner's workbook for you air geekheads out there. But taking typical meteorological conditions, I wanted to ask the question, if you wanted to get to 10 nanograms per cubic meter in air, something of the order of what was measured in the DuPont plant, maybe even lower, how much PFAS per year emissions would you need to get to that level? And the answer at the bottom there, without going through the details, is you only need about 70 pounds per year to get to a PFAS level in air that's well above background levels that have been measured in other areas. 70 pounds per year, since most PFOA was probably released as particulate matter and regulated as particulate matter, 70 pounds per year is trivial. It's far less than a ton per year. So this wouldn't even need an air permit to release that much PFAS, because we don't directly regulate PFAS emissions. I wanted to back calculate from some case studies what air emissions might be. There, until recently, EPA didn't have any real methods published to measure air emissions. And, there have been some measurements taken. Usually those were after controls were put on plants, but probably the best study plant was, again, the DuPont plant. And the estimates there were that there were more than 10,000 pounds per year, far more than that 70, released from that plant each year over, kind of a 50-year period, peaked about 34,000 pounds per year in 1999. ChemWar, before they started putting a lot of controls on the plant, got up to about 3,000 pounds per year of Gen X emissions. If you added them up over various places of the facility, that's what NCDEQ estimated. Smaller sources, though, like chrome plating facilities, could still have some PFAS emissions. And again, the pounds per year matter here. It doesn't take a whole lot of pounds per year based on that last source to basically increase concentrations in air to the point where you might worry about atmospheric deposition. I want to shift the last few slides to soil, and I think I've got to move through these kind of quickly, but there are background levels of PFAS in soil, and I was part of a study where we measured them in Vermont. The bottom line here, and I'm going to put them in the part per trillion range. Remember, we talked about 10 million parts per trillion near an active PFOS source, a refinery, fire training area. Background levels are much smaller. They're on the order of, say, 1,000 parts per trillion if you add the PFOA and PFOS together. And this was a study from the literature that kind of looked at the same question: what are the levels in basic soils? And they found slightly lower levels based on a survey of across the country and actually in places in across the world. Check out that Washington et al. Paper from 2019 if you want to learn a little bit more about PFAS. I think what we see in soils right now is residual PFOA and PFOS because it was used for 50 years, but we're still emitting compounds like fluorotellular alcohols, replacement PFAS compounds, that will degrade into stable PFAS and will continue to cycle through soils. And that's what the paper was trying to figure out, is how large that source might be. Comparatively, we're still in the hundreds of parts per trillion though from a background level. As the analytical methods are getting better at extracting PFAS from soil, the net point here is that if you go out and you measure PFAS in soil, and even if you don't have a source, you might be seeing it just due to background. So I want to talk about soil being that critical reservoir. I think it is. And I wanted to, again, kind of estimate how long does it take to contaminate soils to the level you might care about, and ask the question, how long would it take to get to 10,000 nanograms per kilogram, or 10 ppb of PFAS in soil, which would be kind of a level that you might think might be source impacted, contaminated to a depth of 1 meter. If it took a bulk density of 1,500 kilograms per meter, what I'd find is if I had 10 nanograms per meter in air, which we might get around a point source, you need about 2 years to basically get to that level. So you don't need long at all to accumulate that level. Another last order of magnitude model here is, what about regional PFAS deposition? A lot of it's long range transport, and we're seeing, we think, PFAS in Vermont from sources across the country. And I think that's true countrywide. Just did another back of the envelope calculation to ask the question, what would it take to contaminate all soils at sort of the background level we measured, 1 part per billion or 1,000 nanograms per kilogram across the eastern US to a depth of 6 inches? That would require basically 39,000 pounds per year of emissions over a 50-year period, assuming it all stayed in soil and accumulated there. The DuPont plant itself averaged about 14,000 pounds per year. So these are on the same order of magnitude. So it kind of justifies the idea that, the proverbial cat is out of the bag. We've already contaminated soils to some extent, probably worldwide, due to the PFAS use over 50 years. And the compounds don't degrade. So one last example here is a modeling study I'll point to, which is also based on the DuPont plant. But the only point on this slide is that the numbers in air, soil, and water kind of correspond to the numbers I've been talking about around the point source. Air emissions in the impacts in the hundreds of nanograms per meter, soil on the order of 11 parts per billion, 11,000 nanograms per kilogram, is feeding groundwater concentration contamination at 4,000 nanograms per liter in the modeling. The modeling is not perfect, and this is a comparison of levels in soil. You expect, surface soils to be most impacted by these types of sources because that's where you get first deposition. That's what the model predicted, and the observations also followed that pattern, but there's not great agreement here. And the problem there is that these are, models are tough for PFAS. I think Zeke talked about how KOC measurements can vary and how important air-water interfaces are. I'd like to say we knew what we were doing in terms of PFAS modeling. I think we're just at the cusp of learning about how to do fate and transport modeling. So it's hard to develop those models. But takeaways here are that atmospheric deposition can be important both globally and locally. Sites might be larger than you think they are based on the release areas, just based on where you think the releases occurred. Even on things like spraying foam, stuff gets up into the air and travels, deposits, and those levels in soil can matter. I think soil is that key reservoir because part per billion levels in soil can feed part per trillion levels in groundwater for hundreds of years if you do that quick order of magnitude analysis. Folks have been talking about the ITRC. I'll put some references to it. If you don't want to go to the web and find them, you can go to those links. But there's so much good information available from the ITRC PFAS team. They've been compiling it. It's kind of the state of the art of PFAS knowledge. And I was lucky enough to contribute to the atmospheric deposition section of those documents. So I'll put in a self plug for that too. And I think that's it.
Okay, thank you for that presentation, Steve. And we do have a few minutes left here to have some Q&A with our panel. For those of you in the audience, if you have any questions, yeah?
Thanks, guys. Y'all did a great job of explaining, all the formulations and the variations and so forth. You alluded, for those who haven't read recently, they've just sampled snow on the top of Mount Everest and found PFAS as much as 26 nanogram per liter down at base camp, which is more than the Florida GCTL. You alluded to polar bears having PFAS. At DuPont, I know some of the workers there, their blood serum had 2,000 nanograms plus PFAS in their blood serum, and I know we all have it. Apparently, we've been measured. There's, to the general public that can read these types of things, there seems to be a disconnect between we would all be dropping dead or something, and these types of levels that seem to keep going lower and lower. I mean, I read about reverse causation. I think that's the right term. Where someone with colitis may show high PFAS in their blood, but it's because they have colitis, for instance, or something like that. I wonder if you could set the equations aside. We understand how you get these variables, and maybe say, do you believe there's a disconnect for the general public that reads this stuff and sort of scratches their head? Is there a disconnect in your mind? And if there is, do you have some general thoughts about where this would go and how we should communicate this to clients or less sophisticated people like myself? And I'll leave that. Thanks.
I can take the I appreciate the disconnect, but let me try to connect. So what we're seeing here, when the toxicity factors are developed and ultimately the screening criterion that get derived from them, their focus is to be protective of the most sensitive individual. So it takes into consideration extra levels of safety, margins of safety. So the levels that we see, let's say in regional screening levels and the GCTLs, they're very low. So when I appreciate your question from the aspect, well, it doesn't seem, we should all be dropping dead theoretically. And those levels are set up to be potential, like preliminary remedial goals to ensure, that margin of safety. One way to try to, put things in perspective, I'm sure, like if we're looking at occupational levels, for example. I mean, if we've all dealt with like various studies, let's say for benzene or with TCE levels, we know that for looking at air regional screening levels from EPA versus OSHA permissible exposure levels, we know there's orders of magnitude difference between those two values. And then we're saying, well, why can't we use the OSHA PEL? Well, one, it's because of a regulatory requirement, because we're dealing with CERCLA versus occupational health. But occupational health levels are typically derived to be protective of the healthy worker, not the most sensitive person. So that's why we're going to see this discrepancy and why we're going to see these really low levels.
Michael Goldstein online, if you'd like to ask your question.
Sure. Good afternoon. Good morning, everyone. Almost afternoon. Can you hear me?
Yes.
Fabulous. Thank you for the opportunity to ask this question. Michael Goldstein with the Goldstein Environmental Law Firm. These technical discussions are very helpful to us as practitioners and to our clients. I have a question that hopefully frames these technical issues in a more human context. And I'm wondering whether any of the presenters have had experience or are aware of any data or studies correlating PFAS exposure, disparate or disproportionate PFAS exposure to minority communities of color, to environmental justice communities.
No, it looks like our panelists have not had experience with that yet.
Thank you.
I would actually add that there are at least some communities that some of the toxicological data are derived from the epidemiological data where there have been higher exposures. I don't think they're minority communities, but you could, for instance, look at the Faroe Island studies that are out there looking at immunological effects.
Could you make those available to the moderator?
I can get a reference to them, yes.
That would be great. Thank you.
Steve, I have a question for you. Your guesstimate of the amount of PFAS and from air deposition that could impact soil and eventually groundwater was shockingly low compared to, say, the TRI, the Toxics Release Inventory threshold of having to report on 100 pounds per year for PFAS. So potentially quite a bit of PFAS could be emitted. It's not reportable, and it could be having an impact on groundwater. Is that right?
Yeah, I would say that the TRI regulations look good on paper in a sense, because they got 170 odd compounds that people have to report on. But I'll be surprised if very many industries actually reach that 100-pound threshold. It's I don't know why they didn't set it, from if I take my health protective standpoint here, at the level where other PBT compounds are set, much lower threshold, but for whatever reason they set it at 100 pounds per compound. So there may not be much reporting at all that comes out of that.
Yeah. Any other questions from our audience? All right, we're at lunchtime. Thanks, everyone.
All right, guys.